Assalamualaikum, we are from Group 5. We would like to present to you and share about the Abdul Halim Muadzam Shah Bridge cable failure incident, which focus on the major cause of the tragedy, which is corrosion. I am Nur Alimiliana binti Ahmad Bakri. Would like to share the introduction of this topic. So, first of all, Sultan Abdul Halim Muadzam Shah Bridge is also known as the Penang Sultan Bridge. Is a dual carriageway toll bridge located in Penang, Malaysia. On 6 June of 2013, a ramp leading to the still under construction Penang Second Bridge at Batu Mau interchange collapsed at around 7 p.m. During a car and two motorcycles under the debris. Unfortunately, one person was killed in the incident. The ramp, which is part of the Package 3A of the bridge project, was built by the contractor Cergas Murni Sultan. This tragedy can be outlined through the following main events, which is during the bridge construction and opening. These events highlight the key moments leading to the discovery of the cable concept, which in 2008, the construction of the bridge began as part of a major infrastructure initiative to connect the Penang Island to the mainland. Originally, the opening of the bridge was scheduled in January 2008. However, it was rescheduled and delayed until November 2008. It was postponed as a result of the problems with site acquisition, poor design, and increased building material prices. The cable issues on the Sultan Abdul Halim Muadzam Shah Bridge had far-reaching impacts across various dimensions, such as safety concern to the people, which the public fears were heightened due to the potential risk of cable failure, which could have led to the catastrophic consequences, including structural collapse and loss of life. Aside from that, we rise up the marine ecosystem concern, which any significant damage to the bridge could have had disastrous effects on the surrounding marine ecosystem, including potential pollution from construction material or debris.
Next, let me look to the type of corrosion that we can relate to our case study. The first one is uniform corrosion. Uniform corrosion happens when the material is continuously exposed to a corrosive environment and then it takes place uniformly across the surface. So it is significant in this case because long-term exposure to the marine environment can lead to the uniform corrosion on the bridge structure, and it might contribute to overall material degradation. The next one is pitting corrosion. So pitting corrosion is a type of corrosion that occurs locally and then leaves the metal with tiny holes or pits. It begins when a protective layer is broken that allows chloride ions in the salt water to concentrate places and start to localize attack. So since the bridge is in a maritime setting, chloride ions have the potential to erupt the steel cable's protective coatings. So when stress concentrates, pits will start to crack and then spread under the tension. Over time, structural components are severely weakened by this kind of corrosion. The next one is galvanic corrosion. Galvanic corrosion happens when two different metals are electrically coupled in conductive environments. While cathodic metal is shielded, the more acidic metal will corrode quickly. Galvanic corrosion can be happen in this case if the cable will join two other metals with dissimilar electrochemical potential without adequate separation. So it is unlikely to be the main reason unless the bridge design included an unsuitable material pairing. After that, crevice corrosions can happen when the small spaces or cracks where oxygen is limited and acidic environment will produce. It usually happens in places where water is stainless steel or on bolted joints. Corrosion may worsen in this case if water and chloride ions are trapped in cracks in cable assemblies, clamps, or junction, and this could lead to stress failures by weakening the anchorages or cable termination. The last one is intergranular corrosion. So intergranular corrosion happens when the incorrect heat treatment leaves the borders more vulnerable to attack along the metal grain boundaries. So it is related to this study if the material is prone to grain boundary corrosion in manufacturing process. When paired with other types of corrosion, it can accelerate total degradation. We move to the mechanism of corrosion. As you can see, this is the electrochemical reaction. So here, at anode, oxidation happens when the iron in the steel oxidizes and forms the ferrous ions, while at cathode, reduction happens when the oxygen dissolves in water and reduced to hydroxide ions. This is how formation of rust can happen, where the ferrous ion react with hydroxide ions and oxygen and then form the rust. In this case, the cables that are made from steel is exposed to such electrochemical reaction in the seawater. So, the chloride ions from the seawater accelerate the anodic reaction, which speeds up the corrosion process. Let's move forward to environmental factors. So the first one we have here is humidity and salt exposure. Since the bridge is in a high humidity coastal area, it encourages condensation on the metal surface. The chloride ions that act as a catalyst will dissolve the protective coatings and enhance the conductivity to speed up the electrochemical corrosion process. We move to the next one is temperature variations. Temperature fluctuation can lead to thermal stress that worsen coating deterioration and cracks, so it's possible for corrosive substances to enter the steel. And the last one is oxygen concentration. When the low oxygen reagents that we found in cracks or under the coatings produce differential aeration, it causes localized corrosion and high oxygen availability on exposed surfaces and encourage the catalytic process. Let's move to the next point, which is materials properties. As you can see here, there are two components and they are steel cable and protective coatings. The material used for steel cable is high strength steel and its properties is high tensile strength. So it is prone to stress corrosion cracking, pitting corrosion and brittleness under the stress. Another component is protective coatings. The material used are galvanization, grease layer and HDPE shells. The properties for galvanization are durable and resistant to corrosion, but over time the sacrificial corrosion eventually deteriorates. While the properties for grease layer are self-healing and water barrier, and it can avoid the ingression of oxygen and moisture. And the last one is HDPE shell. It is resistant to UV and chloride ions and also provide mechanical and chemical protection. However, over time it still can crack. Now, let's see the diagram of corrosion mechanism. This is the diagram illustrating the corrosion process in high-strength steel cables used in bridge construction. These are relevant images that show the general of damage structure affected by corrosion, since this case is a specific heuristic record and there are no actual photographs provided. The flowcharts here showing the progression of the incident. So it started when the Sultan Abdul Halim Muadzam Shah Bridge officially opened on 1 March 2014 after overcoming various construction challenges. Next, following its opening, regular inspections were mandated to ensure the structural integrity of the bridge. So in mid-2017, concerns regarding the cables began to surface, prompting further investigation. Authorities initiated investigation to assess the integrity and safety of the cable system. And after that, investigation revealed vulnerabilities in the cable system, raising alarms about potential risks. To address these concerns, sections of the bridge were temporarily closed for thorough inspection and maintenance work. And to enhance monitoring protocols and structural reinforcement, ongoing safety is implemented. Since the incident, regular inspection have remained a priority to monitor the bridge condition. And this is the flow of incident. So on 1 March 2014, after overcoming several construction delays, the Sultan Abdul Halim Muadzam Shah Bridge officially opened and the routine inspection is started to monitor the bridge's structural. Around 2014 and 2017, initial signs of corrosion are found during the routine inspection, but no immediate action is taken. Certain issues mentioned in the records but still not considered serious. Now we look into the during incident. In mid-2017, rumors about possible problems with the cable start to spread up. The integrity of the cable system has become concern, especially among the engineers and maintenance crew. Next, on July 2017, according to official inspection, several cables have serious corrosion that forces the authorities to have urgent discussion about the safety precaution. On August 2017, additional inspection verified that the corrosion is more widespread than first thought, and some section of the bridge is then temporarily closed for intensive maintenance and inspections. While in September 2017, the necessary repairs and safety inspection are conducted and the bridge is partially closed to traffic. Therefore, the concerns about the bridge safety rises among the public. The last one we look to after the incident. On October 2017, after thorough inspection, authorities take prompt safety precautions such as strengthening monitoring procedures and strengthening structures to fix cable weaknesses. And on November 2017, following the completion of the required repairs and the strengthening of the cable system, the bridge is fully open to traffic again. Protocols for routine monitoring have been put in place to avoid it happening again in the future. For 2018 and onward, the scrutiny of maintenance procedures has been increased for significant infrastructure projects in Malaysia, and it is one of the long-term effects. Authority invests in cutting-edge monitoring technologies and commit to more stringent inspection schedules to guarantee structural integrity.
Other factors that can be pointed out are environmental conditions like weather and pollution. Weather such as high winds, heavy rainfall, and extreme temperatures have stressed the cables over time. Airborne pollutants such as industrial emissions may have caused chemical degradation of materials. Next is design flaws. If the cables were not designed to handle the actual loads experienced, they might fail prematurely. Factor is material selection issues. If the materials also did not meet the required specifications, they could have degraded more quickly. Materials with low fatigue performance could have weakened under repeated loading cycles. And for the last factor is operational practices. Excessive Traffic loads beyond the bridge capacity might have caused additional stress on the cables. Poor workmanship during installation could also have introduced defects that contributed to failure. It is likely that the bridge had a maintenance schedule that included periodic visual inspections and structural assessments. However, the adequacy of these inspections in detecting early signs of cable wear or failure could be questioned. For specialized monitoring tools, the use of advanced tools like drones, sensors, or non-destructive testing methods might have been insufficient or not implemented effectively. Corrosion protection measures. The cables were likely treated with anti-corrosion coatings, but the effectiveness of these measures in the marine environment could have diminished over time. Maintenance records also may reveal gaps in regular upkeep, incomplete inspections, or delays in addressing identified issues. Human error during manufacturing is included in material selection. The cables may not have been manufactured from materials suitable for the harsh marine environment. For example, using a steel alloy with an inadequate corrosion resistance or fatigue strength could have been a critical error. For inadequate quality control, errors such as micro cracks, uneven tensioning, or improper galvanization during cable production could have compromised durability. Misinterpretation of corrosion signs might have lacked the technical expertise to identify or interpret corrosion-related vulnerabilities. Reliance on visual inspections without utilizing advanced techniques like ultrasonic testing, magnetic particle testing, or other non-destructive methods might have resulted in undetected internal corrosion.
Next, there is some suggestions that we can do for preventing the similar incident occur in future, which are first improving the materials, better design practices, enhancing maintenance protocol, and use advanced monitoring technology. So firstly, in terms of improving materials use, they should use higher grade corrosion resistant materials such as carbon fiber reinforced polymer, stainless steel or advanced alloys to increase the durability and load bearing capacity of the cables. They should incorporate protective coatings to prevent wear, corrosion and environmental degradation, and then conduct the extensive material testing to ensure performance under various environmental conditions such as in extreme temperatures, humidity and salt exposure. For the next point, which is better design practices, try to optimize cable design using advanced computational modeling to simulate real-world stress and load conditions, which it should incorporate redundancy in the structural design to reduce the risk of total failure if a single component is compromised. Design for easy inspection and replacement of critical components, minimizing downtime during the maintenance. After that, for the purpose of enhancing maintenance protocols, they should implement a rigorous maintenance schedule, including regular visual inspections, non-destructive testing, and load testing. Establish clear guidelines for identifying early signs of wear, fatigue, or structural weakness, and ensure proper documentation of maintenance activities to track the performance history of the cables. Lastly, in terms of advanced monitoring technology, they should deploy real-time structural health monitoring (SHM) system that use sensors to detect strain, vibration, and temperature changes in the cable. Integrate fiber optic sensors to monitor stress distribution and detect potential anomalies before failure occurs. Use drones and AI-driven imaging tools for efficient inspection of hard-to-reach areas. By integrating these recommendations, future incidents can be significantly reduced, ensuring the longevity and safety of critical infrastructure like the Sultan Halim Muadzam Shah Bridge.
As you can see in the table, for the first case is the Silver Bridge collapse, which is located at Point Pleasant, USA at December 1967. Factors is the material fatigue, stress corrosion, and lack of redundancy. Second case is the Sunshine Skyway Bridge failure, which is located at Tampa Bay, USA, and it is when May 1980. The factors have become is where the ship collision, poor cable protection, inadequate impact resistance. The third case is I-35W Mississippi River Bridge collapse, which is in Minneapolis, USA, and the date is August 2007, which the factors is design flaw, excessive loading, inadequate inspections. The fourth case is where in the Genoa, Italy, from August 2018, which is Morandi Bridge collapse. The factors are corrosion of steel cables, lack of maintenance, and material fatigue. And the fifth case, which is the same with our choice of the case, is Paul Severa Viaduct failure, which is in Savona, Italy, from October 2019, which the factors have become this case is from advanced corrosion, insufficient inspection protocols, and environmental factors. Common factors in cable failures have been analyzed, which is environmental conditions. Most cases involve structures exposed to harsh environments, including marine settings, where saltwater accelerates corrosion. Next factor is design and material flaws. By using suboptimal materials or flawed design like the case of Silver Bridge, the insufficient redundancy that can lead to catastrophic failures. Delays in addressing visible deterioration like rust and cracks or inadequate inspection techniques are common contributors. For fatal operational overloading, many failures involve excessive or unexpected loads that exceeded the structure's capacity, as in the 135W bridge collapse, and also human error, mistakes during construction, manufacturing, or inspection phases played a significant role in several cases. Lessons that can be learned from this case are implement advanced real-time monitoring systems to detect early signs of corrosion or fatigue. Use high-grade materials specifically designed to resist environmental challenges such as marine-grade stainless steel. Incorporate fail-safe designs to ensure structural integrity even if one component fails.